Okay, shall we start?
Uh,
Take this out. No. Okay. Okay. So, hi everybody. Today we are going to somehow wrap up the first half of the course. So, the first half of the course was basically about the maximum likelihood and linear models. This is like the conventional machine learning people used to do. And then in the second half, we are getting into, like, we are going to touch a bit of pretty much everything. And before we get there, there are two other notions that are somehow left from this part of the course. One of them is generalization, and one of them is the gradient descent algorithm. So for generalization, we're not going to, I'm going to explain how you can check the generalization of a model. But later on, we are getting at some point, again, back to generalization, where we understand how we can characterize the variance bias trade-off in the model, like how much bias the model could be as compared to the variance they could carry when you are training. But that probably we do it once we are over with the introduction to neural networks. Now, for gradient descent also, I try to just give you the algorithm. I'm pretty sure most of you have seen it in some other courses. Well, if that is not the case, then I guess the introduction we get here is enough for you to just follow what we are doing later. But if you really want to get a bit more detailed into implementation, you might need to take a look and recap some other notions. So let's start with a quick recap what we did last time up to this point. So basically we discussed two different settings. One of them was unsupervised learning. So this was the first couple of lectures we had. So the data set in this case is an unlabeled data set, right? So what you're looking for is basically a pattern inside that data, clustering, and dimensionality reduction. These were the key applications we talked about in the first half of in the first lectures. And the learning algorithm, it was basically looking into the data and trying to find a kind of good model describing the pattern inside the data. This was unsupervised, and we had supervised learning as well, where your data is labeled. And basically what you are looking for is to find out what is the connection between the data and its label. And again, the learning algorithm in this case, what was that learning algorithm? I told you we always do maximum likelihood, right? So it's maximum likelihood. But we also gave it another name when it was about supervised learning, and that was risk minimization, right? So you compute the empirical risk, which is an estimator of the risk you could have, the average loss in that system, and then you basically try to find your parameter such that it's minimized, right? So that was the main idea in both cases, and this is pretty much whatever you do in machine learning always. You're trying to, as I said, most of the time you're doing maximum likelihood, even when you're supervised. But when you're dealing with a supervised case, you can always define the explicit risk, and you are minimizing that one. When you're talking about the pattern recognition or unsupervised learning, you can basically define the likelihood, right? And then you try to maximize it. Now, the algorithm, as I said, for unsupervised learning was the maximum likelihood. And the likelihood, we just define it in terms of the model we consider. We said we assume that the data is being sampled from a distribution like Px. And that distribution, we don't know it, we just parameterize it, right? We assume this is a Gaussian distribution with unknown mean, for example, right? And then this is the parameterized version, and then you try to maximize the likelihood given that parameterized version, meaning that you basically go ahead, compute the log likelihood on every single sample that you have, you average it, and then you try to maximize it on the parameters, right? So we took a look at the clustering problem and dimensionality reduction. And in these problems, we ended up with k-means clustering and PCA. These algorithms were essentially maximum likelihood, right? For a given specific data distribution that we considered implicitly, not explicitly, right? So that was the case. Now, with supervised learning, the story is a bit different. At least it looks a bit different, but in practice, this is the same thing at the end. So we have a data which has a label, and the whole model is somehow describing the connection between the input and output. We usually put a hypothesis on this model, like we assume this connection is linear or nonlinear, and then that hypothesis is going to carry a bunch of parameters. If we want to find it, then we are going to run this algorithm, which is essentially a risk minimization, right? So up to this point, we basically thought about linear models. We talked about SVM as well, right? So linear models basically have a line, right? You get the input, you linearly scale, then if it's regression, you're going to take that one as your label. If it is classification, you're going to do some process to make it into your label. Like, for example, you take the sign, right? So this was the basic things we did up to this point, correct? And we talked last time that we can essentially go to nonlinear models as well when we use SVM. And nonlinear models, basically, instead of using X itself, we are using a higher dimensional feature of it, right? Embedding of it. So we get that guy, we just take it to higher dimension, and then we again do linear classification or linear regression on that guy, right? But when we wanted to just do it for classification using the support vector classifier, then the story got quite simple because we got rid of knowing phi itself. We just needed to know the kernel, right? The cross correlation of this feature phi at two different points, right? And that was a kernel trick, and this enabled us to just somehow train the SVM or find out the right W for nonlinear classification without actually going towards finding the representation, right? Okay, so that was this, and there are two things that we have not yet talked about up to this point, and this is what we want to do today. One of them is about generalization. So basically say that you go ahead, you do k-means clustering, right? Or you do PCA, or I don't know, you do you find the right way for support vector machine. Now at the end of the day, you want to see how well this guy is, right? This is the notion of generalization. It means that if you have a sample data randomly generated, how well it's going to work with that new data, right? So this is one thing that we are going to talk about. We get the idea of generalization. And the second thing is about how we can minimize one function iteratively, because last time we talked about minimization, we had this simple SVC, which was a constraint problem. We could solve it explicitly, right? But I told you, once we just step towards more complicated models, this is going to be over. You cannot find those weights in explicit form, right? And in order to solve that solve the risk minimization problem in that case, or maximize the likelihood, you really need to know gradient descent. This is the only way that you can do it practically. Okay? So these are the two things that we are going to talk about today. Now, let me start with generalization, the first thing. So the main thing in the generalization, as I said, you have found your right model. The question is that how you can test it, right? And you can talk about it very general, but I don't want to confuse you right now. We're going to talk more general when we get into that part explicitly later on. Now, I want to just consider both cases as of unsupervised and supervised learning. When we talk about those, like maximum likelihood and risk minimization, explicitly we see how we can check the generalization. So how do we train in unsupervised learning maximum likelihood, right? So I'm showing here SD, and this D here is your data set, right? So S, if you remember, is the log likelihood, right? When you average it. You remember that? So that log, the term that I showed you earlier, this guy, right? This was what we showed by S, right? And when I write SD, I mean that those samples xn are coming from data set D, right? So I am computing the average log likelihood on data set D. Everybody's cool? SD. This is what I do. And then I try to minimize that, maximize that, right? So if I maximize that 1 over theta, I'm going to end up by theta star, right? This is when I say I've done my training, right? Training is over. Now I have my model. How can I check if this model is doing fine? So you have theta star, right? Well, the classical way of doing it is to find a test set. And this test set obviously should be samples which are independent of the samples inside dataset D. So it means that you cannot go ahead and copy any guy from dataset D into this new set, right? Or you cannot get that guy, compute a function of it, put it here, right? That is still correlated to that guy, right? This means that you should go and find your data distribution, sample from it again, right? If you have images, you need to put a part of it aside, right? Never show it to your training group, right? And if you do that, then you have a test set which is independent of the training set. So you have this test set. It's going to contain I different samples, for instance. And then what you're going to do, you're going to take theta star, exactly the guy that you had trained, found out of training, and then you compute the log likelihood. Okay? So it means that I take every new sample, I put it inside my density function, I find what is the likelihood over the test set, right? And I average it, right? This is what I'm showing by ST theta star, right? Now, one question, if I would have had computed ST as a general, at the general point theta, and I check that, or I try to maximize it, is it necessarily again theta star? Think about it. Yeah. Say, I mean, when I was doing the training, I just computed log likelihood on my training data set, right, D. And then I tried to maximize that guy in terms of theta, right? Now I have that theta star. Now if I do the same approach, I compute the log likelihood on the new set, T, and I maximize it. Is that maximized point, theta, the new point, necessarily theta star? No, right? Now, you would have loved it if it would be, right? Because it's when your model generalizes, right? When the model, you have a new sample, it's working the same, right? So it means that the pattern that you have learned is actually native of the data, right? It's not specific to the data that you have seen already, right? But this is not happening all the time, right? So what you're going to do, you are going to put theta to be theta star in your model, and then you compute your average likelihood, right? And once you have this, you're going to compare it against the likelihood you found during training, right? If they are roughly the same, this means that your model is generalizing. New data, when it sees, it's going to conclude the same pattern, right? This is good. But if you see that this new likelihood you are computing is significantly less than that data set, right? What does it mean? It means that the new samples are not very likely, right? There are two possible cases. Unless you are extremely unlucky when you are sampling for test, that only unlikely guys are coming up, or your training was wrong, right? I mean, the chance of the first one happening is 10 to the power minus, I don't know. You go ahead and compute given the data distribution. It never happens in practice, right? That you just sample and everything you see is unlikely, right? No, they're all likely. Your model is not trained well. So this is when the issue happens, right? So the model is not generalizing. So the pattern, the mean value that it found was specific to those few samples, right? But it's not the true mean value of your process, right? Now, we're going to talk about it later on, but you can think about one simple Gaussian variable, right? If I give you just one sample of a Gaussian distribution, right, and you want to estimate the mean value of that Gaussian process out of it, what is your estimator? If I give you one sample of a Gaussian process, a Gaussian random variable, I just give you one sample of it. It turns out to be 5, okay? Then what is your estimate of the mean value for that 5, right? You have nothing else, right? You take it as the mean value. But what is the chance that guy is really the mean value? Impossible, right? It's probably, I mean, the chance of this one being so far away from your mean value is a lot, right? So it means that the next sample you get to test might be -2, right? And you can think how bad your estimation was, right? So this is the thing that is happening when it's not generalizing. So this is one thing. Now, if you want to think about, for instance, one particular example, we can think about the k-means clustering. And this is what I'm going to do next. But before that, we can use this kind of process to do something called validation. And what does validation mean? It means that, well, if I have a bunch of hyperparameters inside my algorithm, and for what is hyperparameter? For example, in the k-means clustering, k was a hyperparameter, right? You first decide, okay, my number of clusters are 5, right? And then you do clustering, correct? Yeah? So you could use more, you could use less, right? So if you set your hyperparameter, then you can do a trick called validation in order to make sure that that hyperparameter is a fair choice, right? How you can do it? Well, I can take a set V. This set is neither test set nor training set, right? So the data you had the training data D, right? You have a test set T, right? And you have a separate test V, right? These are new samples. Now the test has seen it, nor training has seen it, okay? Now, what you do, you first train your model on D, and then you are going to test it on this validation set, right? Now, out of validation set, you could check if the validation likelihood is far away from your training likelihood. What does it say? It says that your model is not generalizing, right? Maybe the issue is the choice of hyperparameter, right? Maybe if I increase k in my k-means clustering, the model can better generalize, right? Why? Because data had been like in 2 or 3 different clusters, but I assume 2 clusters, right? And then the middle cluster is somehow shared between the 2 clusters that I assume, and it's somehow not very well fitting the data, right? Maybe I should use, instead of k equal by 2, k equal by 3, right? So if that happens, then I can go ahead, change the hyperparameter, and again do this. Again, I train on D, I test on V, I check if they are the same, right? I'm validating. Once I get into a better result, so say I tried over a couple of hyperparameters, and one of them gives me the closest result after validation, then this is when validation is over, right? But even if you validate, it might be that you are fitting to a higher order of data, right? Because you had test, oh, this is not working, you change the hyperparameter, right? You again tried it over validation. This is not working, and finally it works, right? Maybe again it works only for this validation set, right? In order to make sure that your model is really generalizing, you need to get a new test set T, and you should check it on that one, right? If it's again working fine, then it means that the validation was really taking you towards generalization, right? If it's not getting better, this means that, well, that was again fitting into validation sets, right? Was not taking you better, right? Everybody's cool? So, for instance, k-means clustering, how can I do that? Well, in the k-means clustering, when we want to train, we basically compute this guy, right? This was the average distance from the centroids, right? And we showed that this average, or some distance than average, yeah, average distance from the centroids was essentially your likelihood, right, minus your likelihood. So if you minimize this guy, you're essentially maximizing your likelihood, right? This was what you did when you had the training data. And then once this is over, this term, this average distance, is going to be something. I'm showing it by JTrain, right? Now I have this training loss or risk, or training likelihood, minus training likelihood. And then I should check, okay, I go ahead with the validation set and get the average distance on this validation set, okay? And then I compare if my validation distance is significantly higher than my training distance, then I conclude it's not really generalizing. Maybe I go for higher k, right? I increase k. And I check again next time, right? I keep doing it until I see that the distance on the validation set and training set are roughly the same, right? So it means that I had really clusters, and anything coming out of my sampling is in one of these clusters, right? Roughly speaking. Everybody's cool? Yeah. So, but then at the end of the day, you need again to test it, right? Because it might be that you have just a few validation samples, a few training samples, and by playing by k, you're just fitting into what it is, right? For instance, say I validate, I see it's not working, so I increase k, right? If I keep increasing k, at some point, if k is very large, my distance in the training, my training distance is going to be 0, right? If I put the number of clusters to be exactly as the number of samples I have, then every sample has a cluster. The distance for all of them are 0, right? Now, maybe you play with that, and your validation samples are a few, and then it turns out that those points are not far away from your training points, right? And then again, the validation test becomes validation distance becomes very close. But if you try a lot of new samples, then a lot of them happen here and there, right? So there is no reason that when you have done the validation check, it's always confirming your generalization. It's a kind of trick to somehow fix your hyperparameter. Everybody's cool? But we're going to talk about it a bit more. Like, we're going to get a bit more concrete in these notions after we talked about neural networks. Okay. Great. Now, what about supervised learning? So unsupervised learning, we do the same thing, right? We compute the risk, R hat, right? And that one is computed at W star. W star, what is this? This is the guy which is minimizing or risk, right? And what was risk? It was the expected value of the loss, right? Of course, if I have the data distribution, the distribution between y and v, I mean, y is the output of the model, x was the input. So if I do know the distribution of x and v, then I can essentially compute this guy, right? But the point is that I do not have that distribution. We talked about it. The thing that we do, we're going to compute expectation or estimate the expectation over the data set D that we have. What does that mean, ED? It's like you compute loss on every sample that you average it, right? Nothing complicated, right? So this is the empirical risk that we have. Then we minimize it. We find the right weights, right? That was what we did all the semester, right? Now, again, you can define one test set, right? New samples, new images with their label, right? New data points with their label, whether they are green or red, right? Like what we had in SVC. And then you run your estimation, you compute your loss on that training set, test sets, right? Now, if your model is generalizing, supposedly the empirical loss or risk that you are going to get, that guy is going to be very close to what you got during training, right? This is when you say that the model is generalizing, right? But if they are far away, like the new risk you are computing is significantly higher than the one you had during your training, then this means that it's not generalizing, right? And then you need to, again, figure out some way, right? Everybody's cool? Questions? Now, you can again use this idea to do hyperparameter tuning, right? What kind of hyperparameter we can tune in this case? I mean, I can use the same idea as before, as we did with maximum likelihood, to do hyperparameter tuning. But what kind of parameter I have? I mean, I show you here parameter C in the soft SVC, but is there any kind of parameter that you might think of right now? But weights are not hyperparameter. Oh, no. We're not talking about neural network. What? But that is not hyperparameter. That is the parameter of your model, right? Yeah. Anything we had in the course, like, yeah, go ahead. Like the polynomial degree. Exactly, right? Right? You remember when we talked about like model problem is not linear, and then we wanted to go for SVM, you had to choose a kernel, right? And the kernel could have a hyperparameter, right? Like the polynomial degree, it could be the variance of the Gaussian kernel. It could be anything, right? Everybody's cool? So one of the hyperparameters we had, it was when we did soft SVC, right? So you remember what was soft SVC? So we said the problem is not exactly linearly separable, or it's not very perfect because it has a bunch of outliers. Then we just let the points to get out of the margin, or even they have misclassification, right? In order to do that, we came up with this idea, right? You have a training set for all the points, you just solve this problem, right? And what does this problem do? It just solves exactly the maximal margin as before, but it has this extra term. And these Zn that you have in this guy, in this penalty term, they are the one which are somehow softening your margin, right? So you give minus Zn, and if Zn is between 0 and 1, classification is correct, but they get into the margin, right? And if Zn is more than 1, then they start to just jump the other side, right? And this is when the misclassification happens, right? So we talked about it, and we said we cannot really go ahead and find Zn for every single data point because we don't know which guy we should let to get misclassified, which one we should keep on the other side. So the idea was that we added up here, and then we somehow add it as a penalty to our objective using this parameter C. But this parameter C is somehow telling us whether how much misclassification we are letting, how much hard we are on our margin, right? And then if we set C, to be very, very small, then essentially we are getting back to the original, like Z could be anything, right? Z could be very, very large, and then we are basically letting all the points getting everywhere, right? And this was when we had very high misclassification allowed. But if we set C very, very large, then this Z cannot essentially change too much, right? And in that case, this is basically, it gets back to the original hard SVC, right? Now the question for you might be how I can find this C. Well, you can just simply try the validation trick, right? You can solve this problem for some C, right? And once you have solved it, this is probably trying to minimize misclassification given the C that you have chosen on the training data set, right? And then you go ahead and find a validation data set. Now, on this validation data set, you can check how much misclassification you have. This is what I'm showing by E hat V. So E is the error rate, and you are computing it by testing your validation set, right? Every sample inside your validation set, you classify it with your trained model, and then you see whether there is an error or not. If error, count 1. If not, count 0, right? And then you average them. What is the fraction of time you have error on validation set? And E hat D is the fraction of time you have error on your training set, right? If the model is really generalizing, it means that they should be roughly the same and quite small, right? But if you see that on training set you get very well, there's no much misclassification, but on the validation set you get too much error rate, right? This means that your model is not really generalizing. So the line you found, the margin you found was specific to those samples that you had, right? And new samples are just lying here and there, right? If that happened, then you go ahead and change C, right? Change C, try it again, and keep trying till you see that the error you get on V and D are the same. And you can at the end test it to make sure this is really generalization, or maybe again as super fitting on your validation set. Everybody's cool? You got the idea? So this is a kind of way that you should think about generalization, but how exactly we can define it, we're going to, as I said, we're going to talk about it later on. Yes? Training set. Exactly. It's the one which you use to solve this problem, make this problem and solve it, right? But now this is the one that you mean, I guess, right?
Yeah, I was asking if it's everything or just the training.
It's just training, this part, right. Yeah, yes.
When you do the split, when you go back to step 1, like say you change C and go back to step 1, do you reshuffle or do you use the same split?
Oh, we're not, here you don't need to reshuffle, right? It's not neural network with too many samples and gradient descent, right? That is what we do later on. But here, you solve this problem in one shot, right? This is SVC, so you don't really need that. But if we get later on, then actually, again, it's not about shuffling. So you do the whole training, it's over, right? The shuffling happens inside training. And once that is over, then you test, validate, right? If it's not happening, then you get back, and again, you shuffle from scratch, you do the SGD till it converges, and then you check, right? But we talk about it.
Sorry,
Yes.
just clarification. Can you go back to the split?
Here, yes.
So this feels like we're using the 70% to do the training to get the parameters, and using validation to get the hyperparameters.
Right.
It feels like only give us one shot to do the test.
Right, that's one shot.
Okay.
Yeah. Yeah. If you take your test and based on that you do anything on your model, then this is not test anymore. This is again validation, right? Anything gives feedback to your model is just converging your model to that data, right?
But what if the test doesn't give a good result?
No, your model is not working. The problem is complicated, right? If I give you, just think about this example. If I give you random numbers, I just generate a bunch of random numbers, okay? I tell you these are features, and I randomly allocate +1, -1 to them, right? You can go ahead and find a linear classifier for that, right? But there was no relation between those labels and data, right? Now, if I generate new samples, it will not generalize. The point is that your data does not carry any pattern, right? If it's not happening even on the test, then this means that either your model is extremely simple or your data has no pattern, right? What is the connection between the number of times I scratch my head and, I don't know, the number of hours I sleep? Probably nothing. There might be some relations. Maybe I should have given a better example, right? But there are many things in this life that they are not related, right? You can train a model to just get one of them and give you as the output the other, right? But that one probably will not work on new data. This is the whole notion of generalization, right? Okay, so last thing, I guess you already have seen it and we talked about it. Like this is a suggestion that you can do. If you have a lot of data, then 70% you can take in order to do your training, find your parameters. Then you can get 15% to play with the hyperparameters, and then 15% are the last batch which you should use in order to get your test done. Okay? Questions? No question? Okay, great. So if you got no question, yeah, you can take these chapters. I think chapter 1 of Bishop is okay. For chapter 5 of Goodfellow, if you want to take a look, you might wait a bit till we get really into generalization. Okay. Anyways, so that was it. Now, the last thing that I just want to explain, or basically recap, is the idea of gradient descent algorithm. Now, I guess, as I said, many of you might have seen it in different courses, right? Whenever you have optimization, this is the classic iterative approach to do optimization. Now, what is the idea here? The models that we had up to this point, they were all linear, right? And with those models, we were happy because we could find W either explicitly or we ended up, like in logistic regression, we ended up with a problem which had one single minimizer, right? But we could not write it down explicitly. At the end, we just compute the gradient. We set it to 0, right? And this is a system of equations. We can solve it, find the optimal model, right? So for a long time, people were happy with these linear models or even SVM because they say, okay, at the end of the day, SVM is solving a constraint convex problem, which we do know what is the solution, right? But what if we go for more complicated models? For instance, what if I put parameters inside my kernel when I am doing SVM? So we talked about it last time. There is no reason for that guy to be a convex optimization anymore, right? And if that is the case, the issue that is going to happen is that your loss function or the surface that you are trying to optimize, either the loss function or the log likelihood, is going to have a huge number of minimizers or maximizers, right? Let's think we are always minimizing. So it means like we either work with the risk or minus log likelihood. Now, when we are doing this minimization, this is what the phrase that I use quite non-officially up to this point, training. But training simply means that optimization that you solve when you want to find the right parameters in your model, right? When you maximize the likelihood or minimize the empirical risk. Now, if you are doing the training, you always want to find a minimizer. And the point is that your minimizer, as I said, your function might have a bunch of minimizers. And you want to get, I am writing it here, fair, and I'm going to explain what I mean, fair local minimizer, right? Now, if we don't have the final solution, it's not a convex problem like those we solve up to this point, the only way that you can think about optimization is to use an optimizer. And this is one optimizer, right? What is optimizer? You start with a bunch of weights, right? You get those weights, you somehow find out how you should update, right? You get a signal, you update those weights, again you get the new weights, again you get a signal out of these new weights, you update, right? This is the iterative algorithm for optimization. And now, the key point in the gradient descent is they can somehow design this line 3 for us, right? That is the right approach, that is going to explain what is the right approach to update your weight. Okay. So, yeah, we want to just do solve this optimization, and as I told you, this optimization could have multiple minimizers, right? So when we had this SVM or SVC problem, this function was looking like a quadratic function, right? And that guy had only one single minimizer, right? That was cool because you can compute the gradient. You set it 0, that is the only guy who has gradient 0, right? And even if you have constraint, that Lagrange, dual Lagrange could help you to address the constraints as well, right? But in practice, your loss surface could be very crazy, right? So this is the one-dimensional case, but in general, when you think about the loss surface, you should go to a very high dimension, right? So W, your weights, is large, right? Even if you think about linear classifier, it has, what is the size? It depends on your feature, right? If it is 100 dimension input, then it's 100, right? Now, this is a 100 dimensional surface, right? And this is like, a kind of chain of mountains, right? Going up and down here and there, right? And what you want to really find is what is the deepest valley in this chain, right? And you probably guess you can never find it. So the greatest thing you can find is the global minimizer, which is the point where your loss surface is smaller than everybody else, right? But that is typically hard to get there. But you might be okay if you get into a local minimizer, right? This is what I meant by a fair minimizer. I mean, the point which is minimum as compared to everybody around it. Okay? Everybody's cool? Questions? So, you want to get there, and then the question is how you can get there. Well, this is the way that we can build one optimizer with feasible complexity. So let's start with the first step. That is the step size which you want to take to update. This is not important. Line 2, this is your initial parameter, right? So you initially think of your weights to be something random, right? Then you are going to find out one direction. And this direction you shortly see is negative gradient, right? You're going to find one direction. That direction, mu, should be of the same dimension as w, right? Okay? So this is the way, the direction that you should go in order to have your surface dropping. Okay? And if you find that direction, then it's not hard to reduce your loss, right? You can get your weight, and you add it up with the step size that I told you. This is a constant, one scalar. Multiply with this direction, right? It means that you're walking on this landscape, which is full of mountains. You only need to know which direction I should go in order to get into a valley, right? And then you keep walking in that direction, right? And it might be that you start here and you go down, but at some point you see that if I go further straight, then I'm not dropping anymore. At this point, I should change my direction, right? Go in this direction, right? This is the way that you go down to the value, right? So this is what we want to do. So we're not doing anything weird. We're basically doing what a normal human being do, right? Just walking step by step towards what is smaller, right? And we can keep going down, and it might never stop, right? If we just get a direction and go on. How can we stop? We might say, okay, if we get very close to the end of the valley, right, then there would be no much change on the surface, right? If I take one, I mean, when I am really at the deepest point, then if I take a long step even, I'm not changing too much in altitude, right? So this is the point that I stop, right? Maybe each point that I am walking, if I see that my next point is not really changing to the previous point, and it doesn't matter what I do, I'm pretty much stuck. So this is where I would say, okay, I probably got into a valley, right? This is what I mean by this constraint in line 3, right? If your weights in one iteration from the other one is not changing too much, right? Then this means that your algorithm is stopped, right? Question? Everybody's cool? Okay, great. So this is the way that you can design an optimizer. Then the question that is left is, what is the good direction, right? And probably many of you know that a good direction is given by minus gradient of the surface, right? Why this is the case? Well, if you think about a general surface, when you compute the gradient of that surface at one specific point, that gradient is telling you what is the direction, or what is the direction that if you walk in that direction, your loss or your surface is going to increase, right? And not only increase, how you should walk to increase it maximally. So let's take a look at one example. I'm going to show you this in example. So let's consider this example, right? Now, if I am in one particular point on this surface, right? So the surface, so you should think of this blue axis to be the altitude, right? And then it's a big bowl, right? And I want to walk on this big bowl. What is the direction that I should walk in order to get to the top fastest? You should think about, like, if this is x and y, you might see that you should walk exactly in the middle on 45 degrees, right? I can walk like this and go up, right? This is not a cool idea, right? You get it? Right? You see what I'm doing, right? It's not a show. It's real. I'm really talking about the direction. Like, this is the W1 axis, W2 axis, right? I can just jump up like I'm going up the stairs, right? This is the best way I can go up, right? But if I do something like this, I do not just go directly up. I just do, a tilted step, right? I still go up, right? But I go gradually up, right? Like a race car wants to get out of the bowl, right? You can do that as well, but that is not the fastest way to get it out, right? You want to just go directly up, right? So this is the direction, and if you think about the direction is not on the third dimension, right? The direction is on your two-dimensional space, right? It tells you go this direction, you go up, and then, oops, you're taking the highest step, right? So if you want to think about this, take a look at this function, and then also take a look at its counter. And what do I mean by a counter? Just assume that I cut it at one specific altitude, right? I set the function to be alpha, I cut it as alpha, right? That is going to be the counter, the circles, right? Now, what is the gradient direction? What is the gradient of this function if I compute it? It's 2W1, 2W2, right? The gradient, partial derivative with respect to W1, partial derivative with respect to W2, right? Everybody's cool? Yes? Okay, now if you think about this one and you consider the direction is this one. You see on the W plane, right? It tells you whatever the point is, just look forward and go up, right? Don't take any other direction, right? No, do not go to right or left, right? You see my point? So that direction is actually the direction which is exactly orthogonal to this contour, right? Whatever point on the contour you are, just go orthogonal to that, right? Do not take, if I walk tangent to the to the contours, I'm going to go up like this, right? You get it? If I walk exactly tangent to this contour, I'm going to stay in one altitude, right, forever. If I just make it a tiny bit orthogonal, right, just give it a tiny bit of orthogonal component, it's going to get out of the ball, right? But if I want to get out of the ball fastest, I should really walk orthogonal to that, right? This is the direction of gradient. Everybody's cool? You see what I'm meaning intuitively? Okay, so that is what the direction of gradient is. And what is the amplitude of gradient in this case? This is basically the slope of the plane touching that surface, right? The slope, the amount of, increase that you're going to see. So if the gradient is very large, it means that it's very steep. If it's small, this means that it's quite flat, right? So the direction is telling you go this direction. This is the fastest way you can get out of it. But it doesn't tell you how fast it is. This is the slope which tells you how fast you would get, right? Slope would tell you if you take a tiny step, you might go like 10 meters up or you might go 1 meter up, right? That is the one that the slope is telling you, which one it is, right? But the direction is telling you, well, if you go any other direction, you're going to get a smaller than the maximum one. Now, the maximum one could be 1 or 10, right? Everybody's cool? Questions? So, because of this property, gradient, as I said, gradient direction is the steepest direction on your surface that you can increase your function, right? And if you want to just decrease your function, as we talked about right now, the best way that you can do is to just move in the minus direction of the gradient, right? If the gradient tells you how fast you can, what is the fastest direction to get out of the bowl, minus gradient would tell you what is the fast way to get on the bottom of the bowl, right? Everybody's cool? You see what I'm talking about? Yeah? Okay, moral of the story, this minus gradient is the best direction you can move if you want to decrease your surface, right? And if that is the case, then your update should look like this guy, right? Every time you should, whatever the weight is, you need to compute the gradient of your surface at that weight, and you move in the minus direction of that one. Question?
You said earlier that if you move on the gradient direction, you stay on the same height.
No, tangent to the contour. No, you're doing the mistake. Maybe I was too fast. The gradient direction is the orthogonal direction, right? Like here is the gradient direction. You cannot stay in the, if you walk in this direction, you go up, right? Yeah. So this is the landscape, right? The direction tells me forward, right? If I go forward, my foot will not land the same altitude, right? I go up, right?
What is again the gradient direction?
The gradient, you look at this one, because gradient here is two-dimensional thing, right? You have two-dimensional input, and your gradient is also two-dimensional, right? So it's going to tell you, like, this is the land, this is the ground, right? And the surface is the mountain, right? And now, when I talk about the direction, I do not think about the third dimension anymore, right? I would say, okay, I can go here or anywhere around it, right? Which direction should I take? If I take the gradient direction, then when I take my leg and I put my foot back, I am going to be at the highest increase, right? If you think about this bowl, if I don't want to change the height, right, I would just move tangent to the, not the gradient, the counter, right? So I would just keep, keep rounding around myself, right? Everybody's cool? Questions? No question? Okay, now this is the way that we need to update, right? And if you do that update, you are going to always end up with a minimum. This is the point. This is the greatest thing that this guy has. And why this is going to happen? Well, I told you that you are going to stop when your weight is not going to change too much, right? If you want to be very concrete, let's say that I put epsilon to be roughly 0. So it just goes to 0. When that happens, this means that I want this difference between the two guys to get 0, right? And I am going to get 0 with this gradient descent when my gradient is 0, right? So this means the point that this algorithm is going to finish is the point where the gradient of your surface is 0, right? Now, if the gradient of your surface is 0, what kind of point is that? It could be minimum, it could be maximum, it could be a saddle point, right? These are the kind of points on a surface which have gradient being 0, right? Now you can think about every single of them, whether your algorithm is going to land there or not, right? Well, let's say you have a maximum. If I have a maximum and I get at any point around this maximum, right? My gradient minus gradient would tell me go this direction, get out of the maximum, right? So the chance of staying here at the maximum is 0, right? It might be that I start exactly at the maximum and I never update, right? That could happen. But what is the chance that you generate a random point and it's exactly maximum? The chance is 0, right? The chance of touching one point on this plane, it's 0, right? That is not happening. But the point is that anywhere around it, if it happens, I am going to get out of it, right? So the algorithm would never take me to get stuck at the maximum, right? Same thing you can say about saddle point. So on a saddle point, you do know what is saddle point, right? So the saddle point on a multidimensional function, it means the point where your function in one direction is minimized, in the other direction is maximized, right? And the saddle, you know what is saddle, right? The one you put on the horse and you sit on it, right? It is exactly having that surface has this property, right? The one in which you put your leg on is maximized, right? At the center of the saddle. But when you look from the side to the horse, it is minimized, right? You get my point? And that point also has gradient 0. Because if you want to plot a tangent plane, this is exactly horizontal, right? But that is neither minimum nor maximum, right? You get my point? Everybody's cool? No? Okay, at that point, I mean, it's the chance always that you exactly touch that point and this happens. But the key point here is that in one direction, again, say for example, in this two-dimensional case, in one of the directions, your surface is maximized, right? And as long as you get just around that point, since the gradient on that surface is telling you get out of here, it will never remain there, right? Again, the chance is extremely small, so you can practically ignore it, right? And even if that happens, you can just simply do a perturbation, right? You get your point, you see it's stuck, you can randomly just move it around some point, right? And it's going to get immediately out of that point, right? Everybody's cool? So you can do that. You can see that in this your algorithm, the gradient descent, would not finish or would not end up at a saddle point as well. The only case that it can end up is a minimum, right? Because if you are at one point and then you move in the minus gradient direction, it tells you go down, 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 down till you hit the minimum, right? Now, even if I get that point and I just perturb it around, right? It's going to get again back there, right? So this minus gradient is like the magnet. It's going to always touch the minimum, right? It doesn't matter what I do to the point. It's going to get back again to that point, right? And because of that, the gradient descent algorithm is always going to keep you at the minimum. this is the key feature that we are so much interested on gradient descent. It just needs gradient, which is not that complicated to compute, and at the same time is able to minimize your function, right? So this is the way that we are going to complete the algorithm. So everything as before in a general optimizer. The only thing that we do, we are going to update every time with the minus gradient, right? Everybody's cool? So every time you get your weights minus some step size times gradient, this is your new weight, right? And if you keep on doing this, you're going to end up with the minimizer. Trust me, I have done it so much in my life, you never end up anywhere else. No? Okay. Now, this eta that you see here, this is what we call it learning rate, which is basically the step function in this algorithm. Probably we talk about it once again later on. One thing that is happening in practice is that in practice you do not necessarily use the most basic form of gradient descent, like you really get the gradient and you really update with that one, because you are doing things like a stochastic gradient computation, and we're going to mention it later on. But in that case, you are almost always, you're using a gradient-based optimizer. And what does that mean? That means that you have the same algorithm, but instead of having the gradient itself here, you have some computation out of gradient. So what is that computation? Anyone has idea? Anyone has heard of anything we do here? So, for instance, it could be a moving average. This is what you do in Adam algorithm, right? So why we do those stuff? Because the gradients that we get at the end of the day, we cannot compute the exact gradient. We compute an estimator of the gradient, right? And that guy could be noisy. Then we might use some tricks to reduce the noise. I do not expect you to get exactly what I'm talking about right now because we have not been there, right? But once we get there, I'm going to mention it again, and you probably understand it. But you can go ahead and check the details of the different optimizer. At the end of the day, all of them use gradient, right? But they might do some operation on that gradient before they do the update. So this is usually a linear computation. As I say, is the moving average, something like that. But we're going to talk about this later on. Any questions? No question? Okay, so one last thing. I mean, you remember this guy, right? This was the risk we had when we wanted to train the linear regression model, right? And you might be interested to see what's going to happen if instead of computing the gradient and setting it to 0, what's going to happen if I do gradient descent, right? I mean, you can guess this is going to be the same result, right? But you can write it down. How does it look like? Well, if I compute the gradient at one particular point, this is going to be this term, right? 2 times xx transpose, as we have x here, w minus x times v, right? This is the gradient that we have. And then if we want to update, what we're going to do, we're going to get our new weight to be the previous weight minus this term, right? Correct? And you can factor it out, right? You can factor it out. You can say Wt is common between the first and the second term, so you can write it down in this form, right? Everybody's cool? So this is the way that your gradient descent would update. So you get your weight. Again, you multiply it to that matrix out of that bias. This is the new weight. You repeat this till it converges, right? It means that this guy never changes, right? And if you want to see where is that point, well, this is a linear recursive equation, right? You can simply find out where the point, where is the convergence point. You can simply say that, okay, I want Wt plus 1 to be roughly Wt. It means that Wt is not going to change if I do the update, right? Everybody's cool? And then this means that this term inside the brackets should be 0. This is basically gradient, right? When the gradient becomes 0, that terms become 0, you don't have any update, right? And you write it down, or even you write it down on the other recursive equation I showed you, you end up having the same term as you had before, right? There is no magic here because there you set the gradient equal to 0, and then you trusted the fact that the function is quadratic, right? And then this point is actually the minimizer. But here you don't need to check it, right? You just update and it's going to get there, right? Here in this problem, this is definitely the point that the gradient descent ends up, right? But if your surface has multiple minimizer, one of them is being the point that your gradient descent algorithm is going to end up, and this depends on where you start, right? Everybody's cool? Questions? No question? Okay, so I just wanted to give you this quick recap just in case that you have forgotten the gradient descent, because once we start with the neural networks, you need to understand why I am always interested in computing a gradient, right? Because the gradient is simply telling me where to go in order to minimize, and that means where to go to train my model, okay? Now, one thing, logistic regression you remember, right? And in that one, we could not compute the gradient, the model explicitly, right? You either want to solve the system of equations, but easier, compute the gradient and move in the minus direction, right? If you iterate, you're going to end up there, right? And it's not hard to see that that algorithm is the iterative solution to the linear system of equations you wanted to solve.